Hello, I'm Inês, and I'm an application engineering team leader at Materialise. In this video, I will show you how to assess the aortic valve to plan for a TAVI procedure. Transcatheter procedures are transforming the treatment of heart valve conditions, especially aortic valve stenosis. This transcatheter aortic valve implantation, known as TAVI, is still a fairly new technology, and there remain many challenges where precise preoperative planning is key. To assess whether a patient is an appropriate candidate for TAVI, imaging and several measurements need to be performed. The Mimics Innovation Suite can play an important role in assessing a candidate's suitability for TAVI. In this case study, we will go over several workflows that can help evaluate a pre-TAVI case. The areas we're going to cover include heart segmentation, segmentation of calcifications, fluoroscopy simulation, calculation of an SCurve, advanced measurements and analysis, and finally, design and preparation of a pre-TAVI model with calcifications for 3D printing. Please note that the dataset used for this tutorial has an artifact. There is a phase shift in the imaging in a location at the aortic arch. This will have an impact on the final results. To perform the segmentation, we're going to use the CT Heart tool. We will briefly go over the steps involved, but if needed, you can find a more detailed explanation about the tool in another video. To start, adjust the bounding box so that it only covers the heart and select a threshold that includes the blood volume. Place seat points in the chambers to optimize the segmentation. When it's done calculating, verify that the masks are correct. If not, redo the previous steps to recreate them. Since we're mainly going to focus on the left heart, we only need to edit the left atrium, left ventricle, and the aorta. Use the Edit Mask tool and cut off any unnecessary pieces in the 3D view. Perform a region growing operation to remove the floating pieces. You can then edit the aorta using the same Edit Mask procedure. You can see that the aortic valve in this example is heavily calcified. We're going to make use of the multiple slice edit tool to improve the segmentation of the leaflets. To remove sharp edges from the aorta mask, select the Smooth Mask operation twice. Later in the workflow, we're going to create a model for 3D printing. The calcifications can be printed in a different material, and to do that, we need to segment them as a separate object. Make a new mask and adjust the threshold values. Perform a region growing operation 2 times to separate out the calcifications. Models we'll use for the rest of the case study. If we look just at the aorta, you can clearly see the calcifications. SCurve calculation and fluoroscopy simulation. The S-curve, or optimal projection curve, is an important parameter required in the pre-planning of cardiovascular procedures like TAVI or transcatheter mitral valve replacement. Without this, you won't be able to achieve accurate device positioning during the intervention. The S-curve represents all possible angles where the view is perpendicular to the native valve plane. This means that the plane appears as a line in these angles. The fluoroscopy projections used in the clinical setting are the left and right anterior oblique views and cranial and caudal angulation. The S-curve is made by plotting the values of the cranial and caudal angles for step changes in the LAO and RAO angles, which results in viewing the native valve plane on edge or as a line. To create an S-curve, the first thing we're going to do is to draw the aortic plane. The easiest and most precise way to do this is to create a view where the 3 cusps of the aortic valve can be seen together. Using the tool in the View menu, create a multiplanar reslice, or MPR. Scroll through the images and rotate the reference lines until you can see all 3 cusps in the same view. Now, we can easily draw the aortic plane. You can find this tool in the Analyze menu. Make sure you draw the plane in the cusps of the aortic valve, as the accuracy of the S-curve depends on the accuracy of the aortic plane. Once you've finished, go to the View menu, select Fluoroscopy and Create New. This will create a fluoroscopy view based on the AP plane. On the left half of the screen, we'll have the 3 standard image views, and on the right half of the screen, the 3D view with a control panel. Manually save a few angles. In the View Alignment option, choose Reslice Plane. You can either rotate the model and save the view, or slide the bars of the cranial caudal and RAO/LAO orientations to the angles you want to define. Multiple positions or C-arm angles can be saved to provide a clear view of the aortic plane. This can be useful in understanding how the aortic annulus looks at different standard angles on your C-arm. Saving several views perpendicular to the aortic plane is very time-consuming, so we're going to automatically calculate the S-curve using the aortic plane we created earlier. In the S-curve plane option, select the previously created plane. The S-curve is shown in red. Now, we're going to simulate the fluoroscopy view that would be seen by changing the C-arm angle. In the Visualization option, select Simulation. The fluoroscopy simulation tool generates simulated images from the image data based on the angle view position. Select the aorta model to simulate the segmented anatomy. You can change the contrast of the 3D model to enhance the visualization. For example, you might want to make it appear darker, as if it were filled with contrast agent during the intervention. Advanced measurements and analysis. As mentioned previously, the pre-planning of a TAVI procedure is important for assessing the aortic annulus and anatomy of a patient's heart. Measuring the size of the aortic annulus requires a great deal of precision so that the appropriate valve size can be selected and to minimize the risks of leakage. The prosthesis needs to be slightly larger than the size of the aortic annulus to reduce the risk of paravalvular aortic insufficiency. In this next section, we'll show you how to perform several measurements. Use the MPR view you previously created, which you can find in the Reslice Objects tab. The aortic valve has three cusps: the left coronary cusp, or LCC, the right coronary cusp, or RCC, or the non-coronary cusp, or NCC. For the Analyze menu, select the Point tool and use it to mark the 3 points corresponding to the cusps. Relabel these points in the Project Management toolbar to LCC, RCC, and NCC. Now, right-click on the previously created plane in the Project Management toolbar and duplicate it. Move this new plane into the sinotubular junction of the aorta. Using the resliced actual view, create a line to the center of the aortic valve annulus and into the LVOT using the Line tool in the Analyze menu. Create a second line from the center of the mitral valve annulus to the apex of the left ventricle. To better visualize the lines, extend them in the Properties window. Make sure that each line is 100 mm long. Choose the files you want to copy by pressing Ctrl+C on your keyboard. You can then paste them directly into 3matic by hitting Ctrl+V. Under the Measure menu, select the Distance tool and measure the distance between the two planes using the plane-to-plane method. You can then measure the angle between the lines using the line-to-line method. Design and preparation of a pre-TAVI model with calcifications for 3D printing. As we mentioned at the beginning of this video, this patient is going to undergo a transcatheter aortic valve implantation procedure. So now, we need to make a model of the aortic valve, including calcifications, suitable for printing. Although the virtual model can be used for preoperative assessment, with the printed model we can make measurements such as choosing an appropriate valve size or even placing the valve inside the model to verify the size. The first step is to copy all the parts into 3matic. Wrap and smooth the left ventricle, the left atrium, and the aorta. This will clean up any floating noise shells left inside the models. Using the brush mark, mark the sharp edge of the coronary ostium. If you make a mistake, just press Ctrl to unmark. Delete the marked triangles. We're now going to use the Fix Hole Freeform tool to close the created hole. Use Bad Contour as the entity. Merge all the surfaces. Trim the aorta just before the start of the greater arteries. We're only going to include the ascending aorta in our model, so we can have a clear visualization of the aortic annulus and calcifications. Use local smoothing to smooth out any additional rough spots along the aorta and left atrium. Duplicate the aorta by right-clicking on it in the object tree. This model will be used later to design the leaflets. Perform a Boolean union of the wrapped left ventricle, left atrium, and aorta. Make sure to uncheck Remove Original so the original model is preserved in case we need to go back. There may be some floating pieces inside or around the model. To get rid of this, mark the main shell of the part, invert it, then hit Delete on your keyboard. Next, hollow the model until you get a 2 mm wall thickness on the outside. Now trim open the ascending aorta, the branches of the left atrium, and a portion of the ventricle so you can clearly see the valve annuli. Now, we're going to add leaflets to the aorta using the duplicated aorta that we created earlier. Use the Wave Brush Mark tool to highlight the aortic valve leaflets on the duplicate model. Use the Smooth Marking Border tool under the Mark menu to smooth the border around the area you just highlighted and create a new surface. Press Escape and separate the newly created surface into a new part by selecting it while holding the Shift key. Hollow this new part by 0.5 mm in both the inside and the outside directions. The original surface will still be on the inside and needs to be deleted. Find the surface in the object tree and delete it. Perform a Boolean union to unite the leaflets to the rest of the left heart model. Show the models of the calcium to view their position within the aortic valve. The calcifications can be printed in a different material as the rest of the model, but to do this we'll need to save them as a separate STL file, and there should be no overlap with the main model. Start by merging the two surfaces together by right-clicking on them in the object tree. You can select multiple parts by holding down the Control key. Run both the final STL files through the Fix wizard to ensure they're good enough quality to print. Move through the Fix wizard, following its advice until all issues are resolved. There may still be some overlapping triangles, but this is okay. To ensure that there's no overlap of material between the classifications and the rest of the model, perform a Boolean subtraction operation. Now copy and paste the parts back into Mimics. Verify the accuracy of the anatomy by turning on the contours of these parts and scrolling through the images. Once you are happy with your models, export them as STL files. This can be done in either Mimics or 3matic.